VLab. So we're going to be using the entire palette of artificial food colors, and it's derived from just 7 certified dyes from the FDA for use in food, drugs, and cosmetics. So how can these FD&C dyes be identified in a mixture? How do the molecular structures of the dye molecules influence their properties relative to solubility or affinity for different solutions? That's what we're going to find out.
So chromatography is used to separate organic compounds for identification and purification. So an example of that is they use it to find what food dyes are okay to consume and what aren't. And so there's two pieces to chromatography. There's the adsorbent with a D, and it's usually a solid, and it's used to attract and absorb the materials to be separated. And then there's the eluent, which is the solvent, and it carries the materials to be separated through the adsorbent. So it works when the components of a mixture have varying affinities for the eluent, and then you should always take note of the polarities of the adsorbent and the eluent, because a change in polarity could change the attraction of the adsorbent. So we're using paper chromatography, and the paper is the adsorbent. The eluent can be a number of things, and the eluent moves up the paper by capillary action, and the molecules within the polarity closest to that of the eluent will move up the paper most.
So isopropyl alcohol is a fire hazard and toxic by ingestion and inhalation. So the FD&C dyes, they're all hazardous by ingestion and inhalation too, and contact with skin and eyes, so just be careful of what you're touching. Red number 4 is very absorbent in the skin, and then yellow number 5 is also a skin sensitizer. So avoid contact by wearing goggles. Make sure you wash your hands after leaving the lab, and follow the safety guidelines.
We took 20 milliliters of 2% NaCl, and now we're going to put it in this 250 milliliter Erlenmeyer flask. And we're going to repeat that twice.
Meanwhile, using these two dyes, blue and red, I'm adding a dot to the chromatography paper, waiting for it to dry, adding another dot, waiting for it to dry, and adding another dot, to make sure our concentration of the dye is high enough. Good. Make sure our concentration is high enough that we can get some nice results. Just the bottom touches. We don't want the dye to touch the solvent directly, otherwise it'll just go into the solvent. And then we're going to record how far up it goes.
We just ran a second trial of the paper chromatography, but instead of just using the 2% NaCl solution, we used 2% isopropyl alcohol, and then we mixed the two, NaCl and the alcohol, to create the third solution, and we ran it, and it created a pretty piece of paper.
That's just in the NaCl solution, which it's interesting because in the NaCl solution, the colors didn't separate. In just the alcohol, they separated completely, and in the mix, they stayed together, but it's like a gradient of color. Cool.
Of the analyzing, you can see the 3 bands of color. The yellow actually moved up, and then 3 RF values that are calculated by taking the distance from the point of start to the highest part the eluent goes, and divided by the distance the dye travels, which is exemplified in the example calculation for red. And for part 2, we can see how the bands moved depending on the different elements. For the middle one, we couldn't decide where the element actually went up to, so we don't have an RF value for those. Regardless, it's clear that the third trial with the isopropyl alcohol was the best for separating the colors.
The first question, how does the attractive forces between molecules change in the transition from the gas to the liquid to the solid? It's just, in general, they become stronger as you change between phases. In this chart in your packet, the strongest forces are from the icosane, and the weakest forces are from the methane. And to sum that up, for part C, the larger the molecule, the stronger the attractive forces are. For part A, so you have the structure in your packet. Identify the groups in the dye that will bind to ionic and polar sites in the fabric. Well, you have minus O3S on the left side of the structure, and it binds with ionic sites in the fabric because this side has a negative charge, and it will attract positively charged anions. Negative O3S will also bind with polar sites because negative O3S is a polar molecule, which will attract other polar molecules. Still part A. The plus N on the right side of the structure binds with ionic sites because it is positive and will attract negative cations. The NH bond in the center of the structure will bind with polar sites because it is polar. For part B, meet the following if-then hypothesis to explain how the structure of the fabric will influence the relative color intensity produced by methyl orange. If a fabric contains more ionic and polar groups in its structure, then the intensity of the dye color due to methyl orange should increase because there are more parts of the methyl orange where the fabric molecules can bind. And for part C, using this hypothesis, predict the relative color intensity that would be produced by methyl orange on cotton, nylon, and wool, and rank it. So one is lightest and three is darkest. The lightest would be nylon because it has the least amount of sites where the methyl orange could bind. It is not as polar as cotton or wool, though it is polar. The second lightest is cotton because it has more stops for the wool to bind than nylon, but less than wool. And the darkest is wool because it has the most binding spots, and therefore the methyl orange is the darkest.
A+.
Alright, so what we have done is we took the
Sorry, I needed that.
I think we should be doing the yellow too.
Do you want to?
We could.
Is it really hard to do a third one?
No.
Then just do it.
Alright.
High school chemistry, we swear, okay? Get angry.
Things happen.
Okay.
What are these?
Paper chromatography.
We use NaCl and ibuprofen. We made a 2% solution of ibuprofen.
Isopropyl alcohol.
So we ran a second trial of the paper. Shut up, Paris.
We did another trial of chromatography. But rather than just using, instead of just using the NaCl solution, go ahead, Will. What did we do? Like it's cool, but why? I think he's trying to get to the other side, right?
He's building a bridge.
That was my favorite activity. Oh my gosh, remember our dog thing we invented
It's working.
in Tech Ed?
Who is
This
this
is part
kid?
of the lab.
This
Oh.
is ASAP.
Savgay?
Don't worry about
I
it.
have the PowerPoint.
On the right